In this video, I'd like to go through the homework 1 assignment that has been released for you today. The homework 1 assignment is to do with tape spring hinge. It is actually a contribution of the TA this year, and this is part of his master thesis project. It's a very interesting problem. It's a very applicable real-life example of nonlinearities and how local buckling is introduced into real-life structures. Tape springs are very interesting options, and actually you've seen them before in the form of a common tape measure. So if you keep pulling out the tape measure and then you try to bend it, you would see that you would observe some very strange local buckling modes, and there are some strange behavior that it undergoes. And that is exactly why we want you to study the tape springs in general first, and then we use it as a combination in a hinge mechanism to be used for deployment of objects in space. Most of the times they are used for optical objects, so like telescopes and larger optical measurement equipment, etc. So what you're expected to do is to analyze the nonlinear behavior of these springs so that they are beneficial on a spacecraft. Now they're extremely light, they can be folded and stored away. But when they are stored, they are under a lot of stress. And then once the stress is released, then they unfold and can be used as a strength or a load-bearing structure for these objects. You can see here we've given you a geometric description of the tape spring, and some details of measurements have already been given to you. The idea is to use 2 of these tape springs in your model. So the tape spring generally will look like this on the left, as you see, and using 2 of these tape springs with a certain particular arrangement as shown here. So in this case you see they are opposite to each other at a distance of 25 millimeters, as you see on the right. And in this case, you want to put the 2 of them in such a way that you have the right boundary conditions, right constraints that are applied between them. And when you load them, you should be able to study the nonlinear effects of the geometry. We've also given you some results of moment versus rotation experiments. You are working only for option 2C, so you can ignore the option 3 results. You see that there are some events that are happening over here, which you should also be able to model in your abacus model. And it's important that you also understand the physical meaning of these events and these occurrences. Please read through the assignment very carefully. All the description is given to you, how you're supposed to make it. Of course, the geometry and other things we trust you to develop on your own. The rest of the information is provided to you, especially with respect to the reference points. This is really important. Further, once you have made your model, you have to run this using the Newton-Raphson method with an automatic stabilization factor. The automatic stabilization factor has been a topic of discussion in the classroom lecture as well. This is consider this as an example where you use this and understand what it's doing. I've already given you the theory that you're supposed to use behind this. So this should make it much more interesting than a standard problem. You have to compare the results, of course, and report your findings. This is a set of very useful tips. Please read them very carefully and answer all the questions in the report, in the results sheet. The results sheet has 5 questions. You may see that the points are very low, like 1 point, 3 points, 4 points for a lot of work you're doing, but it's all relative. Okay, so don't worry about exactly what grade you get. In the end, it will all be scaled to the out of 10 grade. The first question, you have to describe the model. In the second question, this is related to automatic stabilization, so it includes a bit of theory that you have to answer. And then using the theory, how do you understand, how do you prove that you're using the right factor, etc., has to be given here. Then you have to describe your mesh convergence criteria. This also is something I trust you to do. Of course, start with a coarse mesh and then go on to a finer mesh. Then you have to report the number of increments and you have to tell us why they are large and small in certain areas. Finally, you have to report the moment and rotation behavior for the mesh and stability converged result. When I say stability, I mean the nonlinear analysis using Newton-Raphson itself. From this graph, you will see the major events that I've already pointed to before. Please make sure that you present the justification for each of these occurrences as you understand, from a computational point of view as well as a physical point of view in the problem. Make sure you read the reference that has been given to you, one particularly, and of course the other one can also be found commonly on the internet. Please go through them if it gives you some more information, some more help in answering the questions. See you in the classroom, and I hope you will work through this problem diligently. You have 2 weeks, so don't rush through it. Go through it step by step, and if you have questions, you know you can discuss it over the discussion board.